the class website a little bit. All right. So we're talking about inverse trig functions today, though, which means that we're going to be switching the input and the output, right? So we're going to use inverse trig functions mostly to figure out what an angle is given a ratio of side lengths of a right triangle. So that's our goal with inverse trig functions. And you guys use these a lot in geometry. Okay, so if you take a look at your unit circle, I have a question. What is the angle whose sine value is 1/2? So if you look at the unit circle, you look around the unit circle at those ordered pairs there. What ordered pairs have a y value that is 1/2? Remember, sine corresponds to the y values on our unit circle, right? And there should be a couple. So we should see 1/2 at 30 degrees or pi/6 radians. There's also another place, right, over at 5 pi/6 radians or 150 degrees. We also have an angle whose sine is 1/2. The issue is this. If we were to use our calculators to help us figure out what angle has a sine value of 1/2, our calculator is only going to give us one answer. Okay, our calculator will give us 30 degrees, not 150. So we need to figure out or find a way to know which angle we are going to correctly represent the answer with. Okay, so we're only looking for one answer here, but we know looking at our unit circle, there are two places on the unit circle where sine is 1/2. So take a look at the sine curve. I've got a sine curve graphed here, right? And the question again is, what angle gives us a sine value that is 1/2? Now, if I draw the line, the horizontal line, y is equal to 1/2. That should be down a little bit. Let's try it again. Right? I see that is not a straight line, but imagine it is. There are many places, many angles where our sine curve intersects that horizontal line 1/2. Can you guys see my writing now? Yeah, good. Okay. But only one of those answers is what we're going to report, right? On your homework assignment, we're only going to list one of those angles. I don't want all of them because sine goes on forever and ever and ever and ever. Okay, so we're going to figure out how we do that. Well, we do that by using the inverse function. Okay, inverse sine, inverse cosine, inverse tangent. Those inverse functions are going to allow us to figure out the angles. You guys use these in geometry when you guys were looking for angles as well, probably mostly with a calculator. But there's a problem. In order to invert a function has to pass the vertical line test to be a function, but it has to pass the horizontal line test in order to be invertible, in order to have an inverse. We have a problem with sine or cosine or tangent. None of those functions pass the horizontal line test. If I were to draw a horizontal line across this sine curve, we would intersect at more than one point. So technically, sine is not invertible. But what we do, we want to use the inverse sine. It's going to be very useful for us. So I'm going to restrict the domain of our sine curve. I'm going to restrict the domain to be between negative pi/2 and pi/2. And if I take just that chunk of my sine curve, that piece passes the horizontal line test. That piece of my sine curve is now invertible. I can find an inverse for that piece of my sine curve if I restrict the domain to be between negative pi/2 and pi/2. Okay, this isn't on the notes handout yet, but I would maybe find a place to jot that down. All right, for sine, we're going to restrict the domain to negative pi/2 to pi/2 so that the range of inverse sine is going to be that, negative pi/2 to pi/2. Okay, on the unit circle, negative pi/2 to pi/2, that's here. That's between the first and the fourth quadrant. So visually, we're looking at angles with inverse sine in the first or the fourth quadrant for sine. Right? Because of the way that I've restricted the domain of sine. Now, this is a little tricky. I promise it'll get a little bit easier as we start practicing more and more, okay? All right, so similarly, so then the question is, what angle has a sine value of 1/2? Well, remember that we're now restricting the domain of sine to be between negative pi over 2 and pi over 2. So now there's only one angle in the first or the fourth quadrant that has a sine value that's 1/2. And that is the angle pi over 6. Okay, so that's the only answer that we're going to write on homework or on a test. All right, so similarly, what if I ask this question? What is the angle whose cosine is √3/2? So √3/2 is the decimal value 0.866 something. So let me just sketch a curve somewhere like that, all right? There are many angles, again, where cosine is equal to √3/2. We only need to list one of them. I don't want to know all of them because cosine goes on to infinity. So again, with cosine, in order to invert cosine, we have to restrict the domain of cosine as well. There is a difference though. So what matters right now is that we know this part. To invert cosine, for cosine to pass the horizontal line test, we're going to restrict the domain of cosine to be between 0 and pi. Okay, so for sine, we restricted the domain to be between negative pi over 2 and pi over 2. So it fit the horizontal line test, or it passed the horizontal line test. For cosine, we have to restrict the domain to be between 0 and pi. Okay, visually, where is 0 to pi on the unit circle? Well, 0 to pi is just the first or the second quadrant. So with inverse cosine, our answers are going to be in either the first or the second quadrant this time. Inverse sine will give us answers in the first or fourth quadrant. So cosine and sine, they differ. Luckily, these are the only two things we have to remember, right? Tangent, cotangent, cosecant, and secant, they fit within these same domain restrictions. Okay, so then the question, what angle has a cosine value of √3/2 only in the first or second quadrant now? There's only one. That is pi over 6. Okay, positive √3/2 is pi over 6 there. And that would be the only answer that we write down. Okay, last one. What about tangent? We're going to talk about the reciprocal functions in 7.2. So today we're just focusing on the original 3 trig functions. What angle yields a tangent value? That's 1. Well, there's a lot of them because, again, tangent goes on to positive and negative infinity in the next directions. So we are going to, again, restrict the domain of tangent so that we can take an inverse, so that it passes the horizontal line test. So with tangent, the domain restriction is going to look like sine, very similar to sine. We're going to restrict tangent to be between negative pi over 2 and pi over 2. So that gives us a single curve on our tangent graph. And that now passes the horizontal line test. All right, the only difference I will say between tangent and sine, you guys, is we don't include negative pi over 2 and pi over 2 with tangent because there's asymptotes there. Right? There's an asymptote at negative pi over 2. There's an asymptote at positive pi over 2 for tangent. Okay, so again, with tangent, inverse tangent is going to give us values only in the first or the fourth quadrants. So that's inverse tangent and inverse sine. All right. Inverse cosine is going to give us values in the first or the second quadrant. So we can see that visually. I think sometimes it's a little easier to see than looking at it like this, negative pi over 2 to pi over 2. Okay, this is where trig gets maybe a little trickier than what it was in Unit 6. Okay, so what angle has a tangent value of 1? Well, remember that tangent, we stick between the first and the fourth quadrant. There's only one angle where tangent is positive 1, and that is pi over 4. All right, I would say you guys have a unit circle on the tests and quizzes for distance learning. So have it nearby, easy to access. I think it's always a nice thing to reference. Next year, you will definitely not get the unit circle on testing quizzes though for calculus, so just maybe know that. It's not a bad idea to memorize it. All right, so last thing, when we're talking about inverse trig functions, we use this notation, always that -1 exponent there, that represents inverses. Okay, so the inverse sine, inverse cosine, inverse tangent. Remember that when we're using inverses, then we've swapped the input and the output. So the output now is the angle. The input for the inverse functions is the ratio of side lengths. So we just switch the input and the output of our original trig functions. All right, so there is a way that we can represent or express the same idea. The sine of 30 degrees, if you guys were to look at your unit circle, right, the sine of 30 degrees is 1/2. But we could say that the inverse sine of 1/2, what angle has a sine value of 1/2? That is 30 degrees. So that's how we use sine and inverse sine. Okay, inverse sine we use to find the angle. Sine we use to find the ratio of side lengths of a right triangle. You guys can tell the difference. If you can look immediately at a problem and know that your answer is going to be an angle or a ratio of side lengths, it'll give you a really good idea of where to go. Okay, just being able to identify what kind of value your final answer is going to be makes solving the problem a little bit easier. Okay, so let's do a couple of examples. Stop me if you guys have questions. Your homework for tonight, numbers 13 through 24. So again, you guys are doing only the odds. So 13 through 23, you're going to do like these examples with no calculator. Okay, so inverse sine of 1. So remember, inverse sine is going to give us an angle in either the first or the fourth quadrant. So use your unit circle, figure out where we see a sine value that is +1 on the unit circle in the first or the fourth quadrant. There's only one place. You're getting multiple answers, something's going wrong. It's also a good note. All right, so remember that the y coordinates of those ordered pairs are what sine is represented by. There's only one place where sine is +1, and that is pi/2. We're going to stick with radians today because radians are really, really important for calculus. So most of the time we're going to be in radians this semester. Okay, knowing how to graph and use them. Okay, how about example B? So again, inverse sine, we're looking for an angle in the first or the fourth quadrant where sine is -1/2. So use your unit circle here. Where do we see a y value that is -1/2? There's only one place. That is 11 pi/6. Okay, but there's a problem. Do not box this as your final answer. If you box this as your final answer, it's just going to be marked wrong. Remember that we restricted the domain of sine to be between -pi/2 and pi/2. So in degrees, -90 to 90. 11 pi/6 is 330 degrees. 11 pi/6 or 330 degrees does not fit within this restriction of -90 to 90 or -pi/2 to pi/2. So we have the right angle, we just don't have it expressed correctly. To express 11 pi/6 correctly as our final answer for inverse sine, we need to represent it as its negative angle, -pi/6. Or -30 degrees if we were sticking in degrees. Okay. So just be careful with answers like that. If we've got something in the fourth quadrant, the same will apply for tangent, inverse tangent as well. We're always going to express those angles as their negative angles instead of going all the way around the unit circle. All right, cosine, the inverse cosine of √2/2. Remember, inverse cosine has a range 0 to pi. We need an answer in the first or the second quadrant. So use your unit circle, right? What angle has a cosine value of -√2/2? There's only one, 3 pi/4 there. Okay, I'm going to skip D for a minute. You guys are going to do that on your own in just a second. I want to talk about E really quickly. So E, the inverse tangent of negative root 3. The question is, what angle on our unit circle yields a tangent value that is negative root 3? Okay, inverse tangent has a range of negative pi over 2 to pi over 2. So we're looking for an angle in the first or the fourth quadrant where tangent is negative root 3. There is one problem, maybe more than one, but the square root of 3, like by itself, does not show up on our unit circle, right? So I'm going to express negative square root of 3 as something else, as side lengths that we would see on our unit circle. So I'm going to say this. Negative square root of 3 unsimplified looks like this, using values from our unit circle. Negative square root of 3 is the same thing as saying the square root of 3 over 2 over 1/2, where one of those values is positive and one of those values is negative. That's unsimplified, right? You would never leave a final answer like that, but I'm going to unsimplify it to hopefully make it easier for us to see what angle we're looking for here. Okay, remember, we're dealing with tangent here. So we are looking for an angle on the unit circle in the first or the fourth quadrant where the y value is root 3 over 2 and the x value is 1/2, and one of them is positive and one of them is negative. This is a very loaded question here. Okay, so there's only one place on the unit circle where that is true, where y is the square root of 3 over 2 and x is 1/2 and one is positive and one is negative, right? Find it. Should be 5 pi over 3. But remember, 5 pi over 3 does not satisfy the range of inverse tangent. It's not between negative pi over 2 and pi over 2. We've got to express it with its negative angle. So negative pi over 3 is our final answer here. Okay, try D and F, you guys. D and F. I will go through those answers in just a minute. Okay. I will start calling on people, not today because it's Monday and we're just getting back from break and we haven't done a whole lot of live Zoom lectures, but just note, I will definitely have some popsicle sticks ready to go. Let's do this though. For D and F, just for time's sake today, D should be pi over 6. That is the angle on the unit circle in the first or the second quadrant for inverse cosine. And then F is pi over 4. Right? Tangent is 1 and pi over 4. All right, find your calculator. The next set of examples you guys are going to do with a calculator. Same thing for numbers 25 through 35 on your homework assignment. The only thing I need you guys to do, everything else is pretty straightforward. Just make sure your calculator is in the correct mode. So make sure your calculator is in radians, and then I would suggest just trying it out so that you're good to go for your homework assignment. Okay, the inverse sine of 1/3. If you're in radians and you type in the inverse sine, so inverse sine is generally for most calculators, if you hit the second button and then sine, second sine is going to give you inverse sine. You should be getting 0.34, right? And that's radians. You don't need to write that, but it's just nice to make it clear that that's an angle. Okay, and then just to check your work, make sure your calculator looks good, right? The inverse cosine of 0.44, that should be 1.12. Again, radians, it's an angle. Inverse sine, inverse cosine, give us angle measures. And then lastly, inverse tangent of 3, that is going to be 1.25. Okay. One last thing before we move on to the next couple of examples. This is going to come up in just a minute, but it'll be easier if we use our calculator first. Type this in, please. Evaluate this on your calculator. Tell me what we're getting. Okay, please nod if you're getting a domain error. The calculator smart enough? Yeah, okay. So here's what's going on, right? There's no answer here. The inverse cosine of 1.8. So this question is asking us what angle, because it's inverse cosine, our final answer is going to be angle, what angle has a cosine value equal to 1.8? Okay, that is at the core what this problem is asking. So let me sketch the cosine curve really quickly. Cosine curve, something like that, ish. Okay, looks a lot nicer when you use a graphing calculator. The maximum of cosine and the minimum of cosine, -1 and 1. The amplitude of cosine is 1. So this question is asking, where does our cosine curve intersect the line 1.8? It intersects nowhere, because the maximum of cosine is only 1. We can't get to 1.8. So that's where that domain error is coming from, your calculator. Understanding that at its core is really important as we go through some of these more complex examples. Okay. Okay, so consider these problems. We've got the inverse sine of the sine of pi over 3. Okay. Here's what we're going to do. Order of operations, make your life easy. Start on the inside, work your way out. The sine of pi over 3, we're just going to go onto the unit circle, find pi over 3, and the y coordinate there is the sine value. The sine of pi over 3 is √3 over 2. So now the question becomes, what angle gives us a sine value of √3 over 2? Remember, inverse sine has a range of -pi over 2 to pi over 2. So what angle in the first or the fourth quadrant gives us a sine value that is √3 over 2? Well, that is pi over 3. Okay, so in this case, you guys, inverse sine and sine, they cancel each other out, right? And that's what inverses do. They undo each other. It's a good check to make sure that we're doing the order of operations correctly. But it gets slightly more complicated if we look at the next example, right? This would be an easy problem on a test. This would actually be a problem I probably wouldn't give you on a test. Okay, how about this next example? The inverse sine of the sine of 7 pi over 6. Okay. So let's evaluate the sine of 7 pi over 6. Find 7 pi over 6 on your unit circle. It's down in the third quadrant, right? The sine of that, the y value, is -1/2. So then this becomes the angle whose sine value is -1/2. Okay, so again, inverse sine, range, -pi over 2 to pi over 2. Answer needs to be in the first or the fourth quadrant. So using your unit circle, what angle in the first or the fourth quadrant has a sine value of -1/2? There's only one there. That is going to be -pi over 6. Okay, so there was a little bit of an issue, right? In the first example, on the far left, inverse sine and sine, they canceled each other out. We just got that angle that we started with, pi over 3. But in this second example, inverse sine and sine, they didn't cancel each other out. Our final answer was not 7 pi over 6. The reason is this. If I were to graph 7 pi over 6, 7 pi over 6 is down here in the third quadrant. Remember that inverse sine requires an answer in the first or the fourth quadrant. Inverse sine needed an answer in the first or the fourth quadrant. So we needed to find the angle in the first or the fourth quadrant that had the same y value. With sine, we're talking about the y values. So we take this angle, 7 pi over 6, and all we did was we reflected it over the y-axis for sine. And that became the angle that was represented as our final answer. Okay, that's where we get that negative pi over 6. It's easy to do this when I give you guys answers or angles on the unit circle, but in just a minute, we're going to see angles that are not on the unit circle. So we're going to be drawing diagrams, which is what I'm going to check for in your homework as well. Okay, last one here. The sine of 7 pi over 4. So if you find 7 pi over 4 in your unit circle, it's down there in that fourth quadrant, right? The sine there is negative root 2 over 2. So we're looking for an angle in the first or the fourth quadrant whose sine value is negative root 2 over 2. That's negative pi over 4. So in this third example, inverse sine and sine, they technically canceled each other out, but instead of representing the angle of 7 pi over 4, we had to represent it as its negative value, negative pi over 4, so that it fit within the range of inverse sine, right? Always has to be between negative pi over 2 and pi over 2. Okay, so this is where it gets slightly more complicated. What if I'm giving you guys angles that are not on the unit circle? So here's what I'm looking for. No calculators on your homework for numbers 37 through 43. You guys are going to draw a diagram. So I will be looking for diagrams if you want full credit on your homework assignment. All right, we've got the situation. We're calculating the inverse sine of the sine of pi over 8. So something to note, our final answer is going to be an angle because our final answer is coming from inverse sine. So we know that our final answer needs to be expressed in radians. And I'm going to draw a diagram. I don't know what the sine of pi over 8 is. If I'm not allowed to use a calculator, that's not something that's on the unit circle. So I'm just going to draw that angle, okay? So pi over 8, sitting up here in the first quadrant. And this is where your ability to graph in radians is going to become really helpful, really important. Right? Not only for next year, but for this unit. Now remember, inverse sine requires an angle in the first or the fourth quadrant. Do we have an angle in the first or the fourth quadrant? We already do. Pi over 8 is sitting in that first quadrant. So our final answer is pi over 8. Right? That satisfies the range of inverse sine for us. Okay, but we get to the next example and we see this. Again, our final answer is going to be an angle because it's coming from that inverse sine. But I'm going to sketch 5 pi over 8 really quickly. So 5 pi over 8, here's what I know. I know that pi radians, or 180 degrees, is 8 pi's over 8. 90 degrees is 4 pi's over 8. So 5 pi over 8 is sitting here. How I do radians. Inverse sine says we have to have an angle in the first or the fourth quadrant. So we have a problem because 5 pi over 8 is in the second quadrant. 5 pi over 8 is not in the range of inverse sine. So we are talking about sine here. We're talking about angles with the same y value. So I'm going to take this angle 5 pi over 8. I'm going to reflect it over the y-axis to get the angle we're actually looking for. Okay, got to use a little bit of geometry here. This angle is 3 pi's over 8, which means this angle here is 3 pi's over 8. Final answer. Okay, I'm going to do a couple of these and then you guys are going to check your work on some of them. So let's do L and then I'll have you do M. So we're taking the inverse cosine of the cosine of pi over 12. So again, inverse cosine is going to give us an angle as our final answer. Let's graph pi over 12. Pi over 12 is here. That is obviously not to scale. It should be a little bit smaller than that. That's fine. Just sketch it. Inverse cosine requires an answer to be in the first or the second quadrant. Pi over 12 falls in the first quadrant. So our final answer is just pi over 12. With cosine, we're looking for angles that give us the same x value. So go ahead and try M. I'm going to pause this and then I'll show you guys the work in a minute. Okay, so let's take a look at this one. Negative 5 pi over 7 sits in the third quadrant. So remember, we graph negative angles starting on the positive x-axis and moving clockwise for negative angles. So negative 5 pi over 7 is sitting in the third quadrant. But inverse cosine requires an angle in the first or the second quadrant. So we need to represent an angle that has the same x values because we're talking about cosine, but that's in the first or the second quadrant. So what we're going to do is we're going to take our angle negative 5 pi over 7, and we are going to reflect it over the x-axis for cosine. And then I'm going to figure out what that angle is. Okay, so if I take negative 5 pi over 7, I reflect it over the x-axis, that's going to give me the angle positive 5 pi over 7. Okay, so our final answer, 5 pi over 7. For cosine, there was an alternate way we could have thought about this, though. Maybe one that would have made our lives a little bit easier. That is this. Think back to the trig properties from last semester. Cosine is one of those even functions, right? So the cosine of negative 5 pi over 7, because cosine is even, that is the same thing as if we were just to get rid of the negative and make that angle positive 5 pi over 7. And that's where our final answer comes from there, right? So cosine is an even function. Sometimes thinking about it in terms of evenness makes it a little bit easier to approach a problem. Okay, how about tangent? So I'm going to do one tangent and then have you guys try another one on your own. We've got the inverse tangent of the tangent of 8 pi over 11. So I am going to just keep the inverse tangent there. 8 pi over 11, I'm going to graph that though. Okay, so in radians, if you guys are a little bit sketchy on radians still, 180 degrees or pi radians is 11 pi over 11. I can unsimplify that. So 8 pi's over 11, 8 pi's over 11 are going to sit somewhere over here, right? And then I'm just going to make a mark that this angle in here, that is the difference. That is 3 pi over 11. Because if I have 8 pi's over 11, I need to add 3 pi's over 11 to get to that pi radians or 11 pi's over 11. All right, inverse tangent though, inverse tangent requires an angle in the first or the fourth quadrant. First or fourth quadrant for inverse tangent. Our angle, inconveniently, is in the second quadrant. So for tangent, we need to find an angle in the first or the fourth quadrant that has the same tangent value. So remember with sine, we reflect over the y-axis. With cosine, we reflect over the x-axis. For tangent, we're going to reflect over both x and y. Or we just go 180 degrees opposite. Okay. So tangent's the last one, a little bit tricky. If we know that angle on the inside is 3 pi over 11, these are alternate interior angles. So this is also 3 pi over 11. So our final answer is negative 3 pi over 11 there. Okay, try O before I give you guys the final answer on that one. All right, final answer here is going to be pi over 9. Okay, so 10 pi over 9 sits in the third quadrant. Inverse tangent requires an angle to be in the first or the fourth quadrant. So we're going to reflect that 10 pi over 9 over the x and y axis, or 180 degrees, to get pi over 9. Okay. Before we move on to the next set questions.
Question. Why are we reflecting over both the x and the y axis?
Because we're talking about tangent. So remember that we express tangent as the ratio of side lengths y over x. So it deals with both. So in the third quadrant, tangent's positive. So between the first and the fourth quadrant, where is tangent positive there? It's in the first quadrant. So we have to reflect it over 180 degrees. Okay, we're looking for an angle that gives us the same tangent value. So for tangent, reflect over x and y. Sine is just the y values, so that's why we only reflect over the y-axis. Cosine is just the x values, so we reflect only over the x-axis. All right, good questions. Anything else, guys? Okay, so no calculators on this next set of problems either. Okay, but I will be looking for diagrams here. So we're going to draw triangles in order to kind of help us. Now, if we take a look at these problems, these are backwards to what we just did. Okay, so what we just did was the inverse sine, cosine, or tangent of the tangent, sine, or cosine. So the cosine, sine, or tangent function was on the inside. We've swapped them now. So we're taking a look at the inverse sine, inverse cosine, or inverse tangent first, and then we're taking the sine of that. So our final answers are not going to be angles here. Our final answers are going to be side length ratios. All right, so something to note here is our final answers are going to be ratios. They're not going to be written in terms of radians or degrees because they're coming from the original trig function, sine, cosine, and tangent. Okay, so what are we doing? Well, we're taking the sine of some angle. Note that all of this just represents some angle. Inverse sine, that final answer is an angle. Inverse cosine, that final answer is an angle, right? So we're taking the sine of an angle in this example. So let's just sketch that angle. Let's start with a sketch of that angle, and then we can go from there. So I'm going to keep the sine on the outside. I'm not going to touch that. But here's what I want to do. Inverse sine, remember, the range there is first or fourth quadrant. So I am going to sketch an angle in the first or the fourth quadrant that has a sine value of positive 0.8. So sine is positive in the first quadrant. Okay, so I have my angle in the first quadrant, and I'm going to call it theta. You can call it whatever you want. What would make that have a sine value of 0.8? Well, remember that sine is always y over r, y over the hypotenuse. So the hypotenuse of this triangle is going to be 1, and the y component of that triangle will be 0.8, or the height of that triangle will be 0.8. Okay, so I've sketched that angle on the inside. I don't know what it is without a calculator, right, necessarily. We don't know what the angle is. But the problem ultimately is asking us what the sine of that angle is. So we don't even need to know the angle. We've got the diagram to help us out. The sine of this angle is just 0.8. Right? So again, the inverse function and the function itself cancel each other out. We just need to make sure that things fall into the right quadrants. Okay, how about this example? We have the cosine of some angle. Okay, remember that inverse cosine angle is in the first or the second quadrant. So what angle gives us a cosine of positive 1.8? That is an angle that's going to sit in the first quadrant. Right, positive cosine, that's in the first quadrant, between quadrants 1 and 2. All right, what makes this 1.8? Well, remember that cosine is always x over r. So our hypotenuse here is 1, and the x-coordinate of this triangle is 1.8. So now we're looking for the cosine of this. But there is an issue. Does anybody see it by any chance? Anybody brave enough?
It's not supposed to exceed 1.
Say that one more time.
Not supposed to exceed 1.
Yeah, correct. Good. Inverse cosine is not supposed to exceed 1. Remember, I had you guys calculate this in your calculator. You got a domain error because cosine has an amplitude of 1. The maximum for cosine is positive 1. The minimum is negative 1. We can't exceed 1. Right? If we're looking at this diagram, you guys, what do you know from geometry? Well, we know that the side length of a triangle, of a right triangle, cannot be greater than the hypotenuse. And in this diagram, this side length is bigger than the hypotenuse. So this is not a triangle that is real. So our final answer is undefined. We don't have an answer here. So just be careful with examples like that. Okay, how about this one? Last one I'm going to work with you guys. You guys are going to do S before I move on to the next step. I need an angle, right? The inverse tangent of 2. Now, inverse tangent has a range in the first and the fourth quadrant. So where between the first and the fourth quadrant do I have a tangent value that's positive? Well, again, it's in the first quadrant. And tangent is always y over x. So this diagram, right, this angle has a tangent of 2, means that the y coordinate of my triangle is 2, the x coordinate is 1. And then the tangent of this diagram, we don't really care what the angle is because ultimately we're just taking the tangent of that. Final answer here is 2. So again, tangent and inverse tangent, they canceled each other out. Try S. All right, so S becomes a problem like Q, where we can't take the inverse cosine of pi. Pi is just a number, right? 3.14 if you don't like to look at it as the symbol. Our cosine curve is never going to equal 3.14 because cosine maxes out at +1. So again, this is a case where we don't have an answer. We don't have a solution. If we draw that triangle again, we see that the side length here, 3.14, exceeds the length of the hypotenuse, which doesn't work with Pythagorean theorem. Okay, almost there, guys. Last couple of examples here. So on your homework, the bookwork that is 53 through 69, the bookwork is going to say, or the book tells you to find the domain and the range. Skip that part. You're just finding the inverse equation. Okay, so don't do what the book says to do. Just find the inverse equation, and then you're good to go. So we did this in algebra 2. We did this last semester. Inverse functions, you just switch x and y and you resolve. Okay, so I'm going to switch x and y, and I'm just going to resolve for y. That's how we find the inverse equations. So I'm going to add 1 to both sides, divide by 2. Okay, and we're here. We don't have y by itself, so there's just one more step. This might be new, right? To undo sine. It's kind of like undoing a square. In order to get rid of a square, we take the square root. So in order to get rid of sine, we have to take the inverse sine of both sides. Okay. So just like exponents and logarithms were inverses of each other, right? To solve for an exponent, we had to take a log. Sine and inverse sine are going to do the same thing. In order to get rid of sine, we take the inverse sine. So the inverse equation here is the inverse sine of the quantity x plus 1 over 2. And we just box that. Now you can re-represent y. You could call it the inverse of f of x. That's fine as well. I'm just looking to see that you guys got that equation. All right, try u. And then I'm going to walk you through the last 2 examples. All right, inverse equation, inverse cosine of the quantity 2 minus x over 3. You could have put x minus 2 over -3. That's fine as well. Questions on inverse functions? Okay, last 2 examples. So I would consider everything that we've done today would go into like the applications category of trig. So there would be like an applications test in most years, and then there would be a proofs test, and then a solving equations test. The last 2 examples, V and W, they are kind of setting us up to get to that solving equations part of this unit. Okay, so what I'm asking for is the exact value of x without a calculator. So you're going to show all the steps here. So we're going to get x by itself. We've got to solve for x. In order to do that, the first thing we're going to do is we're going to get the inverse sign of x by itself. Okay, it's kind of similar to how we were solving like exponential equations or logarithmic equations. Get the log of x by itself first and then get rid of it. So I'm going to divide both sides by 3. And that's going to give us the inverse sign of x is equal to pi over 3. And then in order to deal with that inverse sign, we're going to take the sign of both sides. Sine and inverse sign undo each other. So that's going to leave us with x is equal to the sine of pi over 3. And then you can use your unit circle from there. Right, the sine of pi over 3 is root 3 over 2. Okay, the last and final example here is one of the trickier ones. It looks more complicated than I think it is. Okay, so anytime you've got like the cosine of theta and the cosine of theta, those are like terms. As long as theta is the same, like as long as what's inside cosine, sine, or tangent is exactly the same, those are like terms that we can combine. So we've got a set of like terms here. Inverse functions work exactly the same way. If I have an inverse tangent of x and I subtract 5 inverse tangents of x, we are left with a total of -4 inverse tangents of x. Okay, so I'm going to combine those like terms and simplify that into -4 inverse tangent of x. Now it gets way more complicated later on in this unit when I give you angles that aren't the same, then you can't combine them. But because we've got x here in both cases, we're good to go. Okay, so we're solving for x, which means the first thing I need to do is just get rid of that minus pi over 3. I'm going to add pi over 3 to both sides. So we still have that -4 hanging out there, but 2 pi over 3 plus pi over 3, it's just pi. And then I'm going to get that inverse tangent by itself. So the inverse tangent of x is equal to -pi over 4. I'm dividing everything by -4. And then last step, in order to get rid of inverse tangent, we got to take the tangent of both sides. So we're left with x is equal to the tangent of -pi over 4. And again, that's where we go to the unit circle. -pi over 4, same thing as 7 pi over 4. The tangent there is -1. Okay, that's a little insight into what solving equations will look like. They get a little bit more complicated. We'll have to like check our final answers, kind of like how we did with exponents when we're solving exponential equations and things like that. But that's what 61 through 67 are going to look like on your homework tonight. Okay, exact solutions there. All right, so here's what is going to happen. If you look at the distance learning calendar, I will have a link to a video here for 7.2. The homework that corresponds with what we just did is what's due tomorrow. That's page 451, 13 through 67. There is answers to all of the homework posted on the class website already. And then the lecture slide notes are here as well if you want to go back and refer to anything. You guys are scanning both the notes and the homework. So don't forget to do the notes and then the bookwork. You get points for each of these things. So don't make sure you're not losing points there. And that's what we're working through today. All right. And then this video will come up this afternoon. Office hours today, regular time 2:35 to 3:30. And then Thursday, find that trig proofs, the trig identities handout and come to class with that ready to go because we're going to be using the trig identities and you have to know the names of them. Okay, so I would say as we go through this unit, the best thing you can do is just memorize those trig identities. You have the piece of paper to use on the test, but if you don't know that the trig identities already exist, it doesn't help even if you have the piece of paper as we get through the proofs. Okay, so tests are timed. And the trig proofs test is tough if you don't have the trig identities memorized. Okay. All right. If you've got questions, you guys stick around. Otherwise, you are free to log off, get started on the homework that's due tomorrow morning, Email me if you've got questions, but have a good day. Happy Monday. Welcome back. And I will see you guys on Thursday.
Thank you.
Bye.
Thank you.
Have a
Thank
good
you.
day.
Have a nice day.
Bye,
Thank you.
guys.
Thank you.
Bye.
So when we reflect, so we tan reflects over the x and y, sine reflects over only y, right?
Yep.
And cosine reflects over x-axis.
Perfect. Yep, exactly.
Just double check.
You got it.
Have a good day.
See ya. How are we doing, guys? Questions? Anybody?
Yeah, I had a question. On the number or the, what was